find the center and radius. Okay, if I do something like this, what you want to do is you want to follow these steps. All right, step one, you want to group all your like terms together. And here's what's meant by this. You want all your x terms together, all your y terms together, and you want to isolate your constants on the other side of the equation. Okay, so when you do this, there's also a note to leave spaces. Okay, so here's kind of what I mean by this. Okay, to group our x terms, we have our x squared and our minus 6x. So we group the x's together. We're going to leave a space, and then we're going to group our y terms together. We're going to leave a space. Then we're going to move our constants over to the other side. Okay, you don't have to draw in that space if you don't want to. I'm just drawing it in to exaggerate, to leave a space there. All right. Once you regroup and just kind of reorganize your equations, what we're going to do right here is something called complete the square. And you guys should have been exposed to this in algebra when dealing with quadratic equations. And we'll come back during the pre-cal prep and we'll talk more about this. But hopefully the way that I introduce it or review it should be a review for you. You should remember how it's done. Okay, the whole point of completing the square is the following. If we can write something in the form of a squared plus 2ab plus b squared, this is called a perfect square trinomial. If we can rewrite each of these groups of x's and y's in a perfect square trinomial, it's going to allow us to rewrite them as a binomial square. Okay, so completing the square allows you to rewrite a three-term expression in terms of a binomial square. Right, here's the pattern that fits for completing the square. You're going to take 1/2 of your first degree term's coefficient, and you're going to square it. Okay, so our first degree term simply means the term that has a variable power of 1. So here's a first degree term, and here's a first degree term. Okay, and we're just looking at their coefficients. So the coefficient of the first degree x is -6. The coefficient of the first degree y is +8. We're going to take half of that number and square it. So half of -6 is -3, and when you square -3, you get 9. We're going to add that value to both sides of our equation. Right, we add it to the left to complete the square. That alone, this process right here, allows you to complete the square. We add it to the other side just to balance the equation. Okay? So by completing the square for the y's as well, we take half of the coefficient, the first degree term's coefficient, so half of +8 is +4, square that, 4 squared is 16, so we're going to add that to both sides. Again, what that did for us is it allowed us to rewrite our expression as binomial squares. Okay, so this left side becomes x, and the nice, easy way to approach this is exactly how we completed the square in the first place. The second term of our binomial square is simply going to be the value we squared to get the 9 is 16. So we take half of our first degree term's coefficient. So half of negative 6 again was negative 3. So that's our second term. For the y's, we get y minus, or in this case, half of our first degree term's coefficient. Half of positive 8 is positive 4. And then we just combine our like terms over here. 9 plus 16 is 25 plus 3 gives you 28. And after you rewrite that as a binomial square, it's written in the equation of a circle form, so we're just going to interpret, or equation of a circle form. We're going to interpret the equation of the circle, and that's our answer. So our center are the coordinates. What value of x gives you a 0 in here? 3, and what value of y gives you a 0 in here? Negative 4. So there's the coordinates of our center. And then our radius is, now again, remember this r squared is what's equivalent to 28. So to find the radius, we square root that. Are there any perfect square factors we can remove from 28? Root 4 times root 7, and root 4 simplifies to 2. Root 7 stays under that radical. Okay, so this is more like what you are going to see. And I guarantee there's going to be a question like this on the final. And it's possible you might see something like this on an ACT, if you take that when you're junior or senior. Okay, so this is a pretty common relationship that you should be familiar with. All right, the last thing that I want you to do here, and then I'll let you use the rest of the time to get to work, and that is, again, looking at the proof. I want you to see if you can. Okay, so after you have your given information, what can justify moving from statement 1 to statement 2? We added 3 to both sides, so addition property. Again, by saying addition property, we're expressing that the same thing is added to both sides of the equation. Okay, what is step 3 an example of? There's a couple different ways you could answer this. David? Okay, so the ideal one is probably to say completing the square. Okay, but what other actual operation did you perform to both sides of this? Okay, so you could also call this addition property. Now, we can call it addition property because are we adding the exact same values to both sides of the equation? Yeah. Okay, so either of those will work for step 3. Okay, what about step 4? What happened here? Nothing on the left, but on the right, we combined our like terms. Okay. Did we use the same operation for the entire combination? Yeah, and what operation was that? Addition. Now, here's the case where, did we add the same thing to both sides of the equation? No, so it's not addition property, it's just addition. We just combine. And again, what's the catch-all for that? If you're working on one side of the equation, if you just write simplify, you're okay. But again, if you can be more specific, that's fine. Addition is more specific. Okay, now, what allowed us to move from step 4 to step 5? What did we do with each of these perfect square trinomials? We rewrote as a binomial square. Does anybody know what that process is called when you move from a polynomial form? Factoring. So what we could justify this as factoring. If you wrote right as a binomial square, that's fine as well. But that's just factoring. And where did we come up with the equation from for step 6? It's the equation of a circle. Okay, now this next one, again, there's some room for interpretation on it. Okay, when you look at these two forms, you can see that r squared and 28 coincide with each other. Okay, so the way that we can describe this relationship, probably easiest just to say substitution. Okay, but you can have different things. There's not anything that's specific to that. But once we introduce this equation, now we work to solve it. What do we do to both sides of the equation here? Square root, and since we do it to both sides, square root property. And then inside of this radical, we take 28 and reduce it to 4 times 7. What's that process called? Once again, it is factoring. So we factor the 28 into its factors 4 and 7. The perfect square factor of 4 can be reduced to 2. The root 7 stays. So what process did we use to move root 4 into 2? So we can either say square root but not property because we stayed just on one side of the equation, or simplify. And then the final step, just to interpret your information. Again, there's not really one particular reason, but if you put interpret the equation of a circle, that's fine because you're just looking at where those fit and you're interpreting it the way that we've discussed.